Hey, welcome back. In this video, we're going to talk about a very powerful probabilistic method called dependent random choice. And we'll use it to prove some new upper bounds on some Turan extremal functions. And when I say new, I mean new to our class, not new to the world. To review, we define the Turan extremal function ex of n comma h to be the maximum possible number of edges in an h-free graph of order n. And in one of the earlier videos, when we were discussing Jensen's inequality, we proved the Turan theorem. And that theorem says that the extremal function, the Turan extremal function of n comma k sub r comma s, the complete bipartite graph with parts of size r and s, that Turan extremal function is big O of n to the 2 minus 1 over s. So the Turan theorem gives an upper bound on that Turan extremal function. And it's an open problem to determine whether or not that upper bound is tight up to a constant factor. There's a more general open problem about Turan extremal functions of bipartite graphs. And it's related to another concept that we discussed in an earlier video, which is degeneracy. And just to recap, we call a graph G K degenerate if every subgraph H of G has a vertex of degree at most K in H. And here is a conjecture from 1984 of Erdős and Simonovitz, and this conjecture is still open. And the conjecture is that if G is a bipartite K degenerate graph, then the Turan extremal function ex of n comma g is big O of n to the 2 minus 1 over k. The conjecture has been resolved for some specific families of K degenerate bipartite graphs. For example, complete bipartite graphs where one of the parts has size k. In other words, the Turan theorem. And in this video, we're going to look at this probabilistic method called dependent random choice. And we'll use it to prove this conjecture for a more general family of bipartite graphs. Specifically for bipartite graphs where all of the vertices in one part have degree at most k, and that word complete obviously should not be there. Though it's not false what that bullet says, it's just not as general as it could be. So let's discuss dependent random choice, first in words, and then we'll look at it more precisely. So what's the general idea of dependent random choice? Well, suppose we have a graph that has sufficiently many edges relative to its number of vertices. In other words, we call it dense. So if we have a sufficiently dense graph, the idea is that we can find a subset of the vertices, and we'll call that subset of the vertices Q. And that subset will be special in that all of its small subsets will have many common neighbors. So in words, that will be the idea of dependent random choice, that in a sufficiently dense graph, we will find a large vertex set in which all of the small subsets have many common neighbors. And when we apply dependent random choice to bound Turan extremal functions of bipartite graphs, we will use the vertex set Q in this last bullet to construct a copy of the forbidden bipartite graph G. So we will build G using the vertices of Q. Now let's look at what dependent random choice says more precisely. And there's multiple versions of it. Here's one lemma that uses dependent random choice. So suppose that x, d, y, n, and s are positive integers. Also suppose that G is a graph of order n with vertex set V and edge set E, and define D to equal 2 times the cardinality of the edge set of G divided by n. And here's the claim of the lemma. If there is a positive integer r such that d to the r over n to the r minus 1 minus n choose s times y over n to the r is greater than or equal to x, then there exists some subset Q of the vertices V for which Q has cardinality at least x. So the x we see here, for which Q has cardinality at least x, it's the same x we see over here in this inequality. And we claim that this Q with cardinality at least x also has the property that every s vertices in Q have at least y common neighbors. So it's not just that we can find a subset of the vertices with cardinality at least x. It's a subset with cardinality at least x such that all subsets of size s have at least y common neighbors. In other words, all small subsets have many common neighbors, like we were saying on the previous slide. In order to prove the lemma, we're going to introduce some notation. We'll define n of v for any vertex v to be the set of vertices that are neighbors of vertex v. In other words, these are the vertices that are contained in an edge with the vertex v and that are not equal to v. More generally, for any set of vertices S, we'll define n of S as the set of vertices that are neighbors with all vertices in S. So here is the claim of dependent random choice. Suppose that G is a graph of order n, D is equal to 2 times the cardinality of the edge set of G over n. And if we can find a positive integer r such that d to the r over n to the r minus 1 minus n choose s times y over n to the r is greater than or equal to x, then there exists some vertex set Q, which is a subset of V, for which the cardinality of Q is at least x, and every subset of Q of size s has at least y common neighbors. I just want to point out here, the y common neighbors here, this is the same as the y that we see right here. Moreover, the s vertices right here, this is the same as the s that we see right here. And like I mentioned before, this x is the same as this x. So let's try to prove this. And in order to prove this, we're going to use an alteration. And To use an alteration, we're going to run an experiment. Here's how our experiment's going to go. We're going to pick a set, we'll call it big R, of R vertices of the vertex set V, so that should be of right there. And these vertices will be picked uniformly at random, but with repetition. Now the set R right here, this is not going to be the set that we perform the alteration on. So we're going to use R to make the set that we want. And the set that we want is going to be defined as P, which is N of R. N of R is what we defined on the previous slide. And just as a reminder, N of R right there, this is the set of vertices that are neighbors with all vertices in R. So the set of vertices that we're going to use and then perform an alteration on is the set P, which is a set of vertices that are neighbors with all the vertices in R. And R was the set of vertices that we drew in our experiment. We're going to define a random variable. This random variable will be named x, and x will be defined as the cardinality of P, the set we defined in the previous bullet. And in order to find the expectation of x, we will define some indicator random variables for each vertex in the vertex set of our graph G. For each vertex v, little v, we'll define this indicator random variable x sub v to be 1 if v is an element of P. Again, the P here, same as the P up here we defined, the set of vertices that are neighbors of all the vertices in R. And our indicator random variable down here will be 0 if v is not an element of P. So it's 1 if v is an element of P, it's 0 if v is not an element of P. And we see, by definition, the random variable x is equal to the sum over all vertices in the vertex set of the indicator random variables, x sub v. And we can use linearity of expectation to see that the expectation of x is equal to the sum over the vertices in v of the expectation of x sub v. And calculating the expectation of x sub v, we can get that, and we can see by definition, expectation of x sub v, it's equal to 1 times the probability that v is an element of P plus 0 times the probability that v is not an element of P. And the 0 part becomes 0. And 1 times the probability that v is an element of P, that's just the probability that v is an element of P right here. And we can see the probability that v is an element of P. So we can think about that. And we note again up here that P is defined as the set of vertices that are neighbors with all vertices in R. So the probability that V is an element of P, in order for V to be an element of P, it means that every vertex that we draw in R must be some neighbor of V. And we can look at that probability for each of the vertices that we draw in R. So for each little r that we draw in R, the probability that little r is a neighbor of V, we can see that that is equal to the total number of possibilities for the vertices that we can draw for this little r? Well, the total number of choices we have is just the number of vertices in our graph. It's graph of order n, so we get n in the denominator. The numerator is the number of possibilities that are successful. The number of possibilities where the r that we draw is a neighbor of v, and that's going to be the cardinality of the neighborhood of v, the neighborhood that does not include v itself. So for each little r and big R, the probability that that little r is a neighbor of v is equal to the cardinality of the neighborhood of v over n. And since big R has a total of r elements, and this is with repeats, and I guess this little r I used here, that's probably not the best variable, since to create r, we draw little r vertices uniformly at random. So I might change this name here, something like little q, just to not have too many little r's around. And I think that makes everything okay. So since in our experiment we draw a total of r vertices, and this is with repetitions, the probability that v is an element of this set P, in other words, the probability that v is a neighbor of all the vertices that we draw, is going to be this probability that we found right here and raised to the r power. And that's what gives us the expectation of x of v in this spoolet. And we can see then that in order to get the expectation of x, we can just sum over those expectation of x of v's. So we get the sum over the vertices in the vertex set v of the cardinality of the neighborhood of v divided by n raised to the r power. And we can pull this n to the r right here to the outside. And that gives us the n to the little r right here. And we have a sum still over the vertices in v, but now it's of the cardinality of the neighborhood of v to the r. And now we can use Jensen's inequality. And we can use it on the function f of x equals x to the r. And we use it because the function f of x equals x to the r is the function that we see right here. And using Jensen's inequality, we have this quantity that we see right here, n to the minus r times the sum of the cardinalities of the neighborhood of v to the r. That same thing down here is greater than or equal to, so we see an n to the 1 minus r right here. So we can write this quantity I have right here as an n to the 1 minus r and then divided by n. And now I'm going to take the divided by n part and put parentheses around it like this, and I can apply Jensen's inequality to the thing in parentheses. So I apply it and I substitute. And that's by Jensen's inequality to get from the left inequality to the right inequality. And then I can simplify, because I can note right here, this sum over the vertices in V of the cardinality of the neighborhood of V. This is just the sum of the degrees of my graph, and the sum of the degrees is just 2 times the cardinality of the edge set of G. And recall that D right here was equal to 2 times the cardinality of the edge set of G over N. So this whole thing in parentheses is just a D. So that thing in parentheses, the parentheses thing can be replaced by D. So we have a D to the R up there. And the n to the 1 minus R, we wrote that in the denominator. And in the denominator, it becomes an n to the r minus 1. So that went right there. And this thing in parentheses became the D. And we can take that all together. So we started with an expectation of x right here. We had a string of inequalities, and they were only going in one direction. So the things on the left were greater than or equal to the things on the right. And we finished up with a d to the r over n to the r minus 1. So we showed that the expectation of x is greater than or equal to d to the r over n to the r minus 1. Now, we're not done yet because we didn't do any alteration yet. So we didn't modify x at all. And x might have some issues. So x is not this set that we're looking for up here, this set Q, the subset of V. Because Q is special. Every subset of vertices in Q of size S has to have at least y common neighbors. And we don't know if x right here, we don't know if x has that property. So it's possible that x might have some subsets of size S with fewer than y common neighbors. So that's why we might want to do an alteration. And we'll do that on the next slide after I clear all this stuff. So there again is our statement of dependent random choice. We're trying to find this subset Q of the vertices of cardinality at least x, such that every subset of vertices in Q of size S has at least y common neighbors. We're going to use an alteration. And so far what we did is we ran this experiment where we picked a set, big R, of little r vertices. And these are vertices of the vertex at V, and we picked them uniformly at random and with repetition. We define P, big P, as the vertices in our vertex at V that are neighbors with every vertex in R. We define the random variable big X as the cardinality of P. And we showed on the last slide that the expectation of X is at least d to the r over n to the r minus 1, where again, d is defined up here as 2 times the cardinality of the edge set of G over n, and n to the r minus 1, the n is the order of our graph G, and r is this positive integer for which we have this inequality is true. We're going to define another random variable in this slide. This random variable will be called y, and it's defined as the number of subsets T, which are subsets of P. So P right here is the vertices that are neighbors with every vertex in R. So these subsets are the subsets that prevent P from being the set Q that we're looking for. So the set Q has every subset of S vertices has at least Y common neighbors. And these subsets down here, they have size S, but they have fewer than Y common neighbors. So these are the problem subsets. And we can suppose that T is some subset of V of size S with fewer than Y common neighbors. So not just a subset of P, but a subset of V, V the vertex set of our graph. And I claim that the probability that T is a subset of P is the cardinality of n of T over n to the R. Let's see why that's true. So we can see for each, let's say, little q that we draw in R, the probability that little q is a neighbor with all of T, and we can calculate that probability. So the probability that little q is a neighbor with all of T. So like the last probability we calculated on the last slide, the number of possibilities for Q when we're drawing the vertices for R we draw with repetition, so there's always going to be n possibilities, n being the order of our graph up here, and the number of successful possibilities, where Q is a neighbor with all of the vertices in T. Again, this T being this subset of size S. That's going to be the cardinality of n of T. Why is that? Well, for it to be successful, it has to be some vertex which is a neighbor with every vertex in T. Vertices that are neighbors with every vertex in T must be elements of this n of T. So these are neighbors with all vertices in T. So that's the probability for each Q that we draw in this set R, that Q is a neighbor with all of T. And so the probability that T is going to be a subset of this P, P being the vertices that are neighbors with every vertex in R, that probability is just this probability we found right here and raised to the rth power. So for P to be a subset, for T to be a subset of P, we need that every vertex that we draw for R has to be neighbors with all the vertices in T. And if every vertex that we draw in R is neighbors with all the vertices in T, we also see that implies that T is a subset of P. So this implies that the probability that T is a subset of P is just this probability we calculated right here, cardinality of n of T over n, and raised to the rth power. And so here's another problem for you to think about. Why is the expectation of this random variable y less than n choose s times y over n to the r? And one thing to think about here is that these subsets that we're counting in y, the number of subsets of size s with fewer than y common neighbors, the key thing about these subsets is that they have fewer than y common neighbors, strictly fewer than y. So assuming that this problem is a true statement and using the bound that we proved on the expectation of x, so combining these two together, we see that the expectation of x minus y is at least t to the r over n to the r minus 1 minus n choose s times y over n to the r. And here's where our assumption up here comes in. By that inequality, we know that this is at least x. And when I say bilinearity of expectation, that's what I used right here. So expectation of x minus y is equal to expectation of x minus expectation of y. And then that's greater than or equal to. So this equality right here, that's the linearity of expectation. And then that gave me this, because again, I know that expectation of x is greater than or equal to this thing right here. And expectation of y is less than this thing right here. And again, that all is greater than or equal to x, and we take the difference by our assumption in the dependent random choice lemma. So we're almost to the end. We didn't perform the alteration yet, but this tells us what alteration we should perform. And before we see that, let me clear that. So we ran our experiment where we picked our set, big R, of little r vertices of V uniformly at random, and again with repetition. We defined big P as the vertices that are neighbors with every vertex in big R, and we defined X to be the random variable that is the cardinality of big P. We showed that the expectation of X is at least d to the R over n to the R minus 1. We define this random variable Y as the number of problem subsets in X. So these are the subsets that prevent X from being the set Q that we're looking for in the dependent random choice lemma. And so Y is the number of these subsets of size S with fewer than Y common neighbors. And in the dependent random choice lemma, we want a subset of vertices such that all subsets of size S have at least Y common neighbors. So we're trying to get rid of these subsets down here. And I claimed in that problem, which I left to you, that the expectation of Y is less than n choose S times Y over n to the R. And that implies that the expectation of X minus Y is greater than or equal to d to the R over n to the R minus 1 minus n choose S times Y over n to the R. And by our assumption up there, that's greater than or equal to X. So that's down here. And finally, we can do our alteration. So our alteration, we just remove a single vertex from each of the subsets T, these subsets T, the problem subsets, of size S with fewer than Y common neighbors. So any of the subsets of size S that don't have at least Y common neighbors, we will remove a vertex from them to get rid of the subset. So if we remove a vertex from the subset, that subset's gone. So that's a way to get rid of each of those subsets. And we can see then, if we remove just a single vertex from each of these problem subsets, the expected size of the resulting set, once we remove each of those vertices, is going to be at least X. And moreover, once we remove each of those vertices, the resulting set that we have doesn't have any more subsets of size S with fewer than Y common neighbors. So once we remove all of these vertices from the problem subsets, we get rid of all the problem subsets. So there's no more subsets that have fewer than Y common neighbors. In other words, every subset of size S has at least Y common neighbors. And the expected size of the resulting set is at least X. So that means since the expected size of the resulting set is at least X, it's possible to find a set big Q of X vertices in our vertex set big B such that all of the subsets of Q of size S have at least Y common neighbors. So here we're just using the fact that if the expectation is some number, then there must be some possibility in our sum that we did for the expectation that is at least the value of the expectation. So now that we have this dependent random choice lemma, we can apply it to the Turan problem that we were talking about earlier. And specifically, that's the Turan numbers of bipartite graphs where one of the parts has maximum degree at most k. In order to work on this bound, it'll help to have a simple bound about factorials, which I will leave as a problem to you. And the problem is to find C, and C must be greater than 0, such that T factorial is greater than T over C to the T for all t greater than 1. So C, I just want to emphasize, is a constant. So find a constant C such that t factorial is greater than t over c to the t, and C must be positive too. So let me write that word as well. So here's the claim. If G is a bipartite graph in which all of the vertices and one part have degree at most k, then the Turan extremal function of n comma g is big O of n to the 2 minus 1 over k. And we'll assume that G has parts, we'll call them L and R, and all of the vertices in R will have degree at most k. So that'll be the part that has all the vertices with degree at most k. We'll say that the variable little x is equal to the cardinality of L. The variable little z is equal to the cardinality of big R. We'll define y right here as x plus z. So this x plus that z. We'll define R to equal k. And we'll let m right here be the maximum of x to the 1 over k. So this x right here to the 1 over k. And the other part of that maximum is c times y over k. Same c we have right here. Same y as right here, that y. And the k's are these k's. So suppose that H is any graph which has order n and at least m times n to the 2 minus 1 over k edges. I just want to note here, this m is a constant. So this m, this max, that's a constant. Because all of these things in the max, the x's, the k's, the c, the y, these are all constants. So this graph H with order n, it has omega of n to the 2 minus 1 over k edges. And we'll say that the average degree, little d of H, that average degree, we can see that that is greater than or equal to 2 times m times n to the 1 minus 1 over k. Why is that? Well, the average degree, so average degree is equal to the sum of the degrees over n. The sum of the degrees over n is equal to 2 times the number of edges over n. And the claim was that there's at least m times n to the 2 minus 1 over k edges. So 2 times the number of edges over n is greater than or equal to 2 times m times n to the 2 minus 1 over k divided by n. And when we divide that by n, we get 2 times m times n to the 1. So the 1 right here, instead of a 2, minus 1 over k. And we can see then that if we take d to the r over n to the r minus 1 minus n choose k times y over n to the r, this is going to be greater than or equal to, so that first part, the d to the r over n to the r minus 1, I claim that's greater than or equal to 2m to the k. Why is that? Well, d to the r is equal to, since r equals k, that's just d to the k, and that's equal to 2m to the k times n to the k minus 1. And when we divide that by n to the r minus 1, recall that r equals k. So when we divide it by n to the r minus 1, here we'll have an n to the r minus 1, I'll squeeze it in there. And then this gives us an n to the k minus 1. Cancels here. Make sure it's clear that that stuff's separated. And so when that cancels, all that's left is that 2m to the k. So that's why we got from here to here the 2m to the k. Now let's look at the other parts of it. So the n choose k, this is less than or equal to n to the k over k factorial. So that's why we can say that negative n choose k is greater than or equal to negative n to the k over k factorial. Moreover, y equals x plus z. So we just substituted for the y, the x plus z. So we didn't do anything that interesting there. And the r equals k, so we turned the r into a k. Nothing interesting there. And we can note there that that quantity is greater than or equal to the quantity 2m raised to the k. We didn't do anything there. But then the other part, so this part was the same. The other part, n to the k over k factorial times x plus z over n to the k. Here we use the fact that k factorial is greater than k over c to the k. And that implies that negative 1 over k factorial is going to be greater than c over k, negative c over k. And the c over k part is raised to the k. And so we can combine that with the rest of it. So we have negative n to the k, negative 1 over k factorial here, and n to the k here times x plus z over n to the k. And so we see that this is greater than, we get negative c over k to the k. We can substitute that for this negative 1 over k factorial. The n to the k right here cancels with the n to the k right there. And we have this x plus z to the k. And so we have a minus, that's the minus right there. We have c over k to the k. So that's a c right here, the k to the k. And then x plus z to the k. That's our x plus z to the k. So that's how we got that. And I'll clear that up a little so we can see the rest of the bullets. And I claim that that is greater than or equal to m to the k. Now let's see why that's true. I claim that that's true by the definition of m. So recall that m is the maximum of x to the 1 over k and cy over k. And so we know that m is greater than or equal to cy over k, which equals c times x plus z over k. So m is greater than or equal to c times x plus z over k. And that tells us then that this quantity right here is going to be greater than or equal to 2m to the k minus m to the k. And it's easy to see that that is greater than or equal to m to the k. And that's why we got that m to the k right there. And the other part of the maximum is how we can see that m to the k is greater than or equal to x. So by that maximum, we know that m is greater than or equal to x to the 1 over k. And then raising both sides to the k, m to the k is greater than or equal to x. Now that tells us that by the dependent random choice lemma, we can find a subset, we'll call it U, of the vertices of this graph H, with the cardinality of U is equal to X, and all subsets of U of size K have at least Y common neighbors. And this should be capital U. And the proof can be finished from here by using the following problem. So let G be a bipartite graph with parts L and R. L will have cardinality X, R will have cardinality Z, and the vertices of R will have degree at most K. And here is what to prove. If H is a graph that has a vertex subset U with the cardinality of U equal to X, for which all subsets of U of size K have at least X plus Z common neighbors, then G is a subgraph of H. So I claim that if that is true, if that problem is true, then we can take the vertex set U of the vertices of H that we found by dependent random choice up here, and in that vertex set U, we find a copy of G. And since we're guaranteed to be able to find that vertex set U, as long as the number of edges is at least m times n to the 2 minus 1 over k, and again, m right there is a constant, that implies that any graph with at least that many edges must contain a copy of G, which gives us the upper bound on the Turan extremal function. That brings us to the end. Thanks for watching.